I like more expectations. The feeling of the tactile inside the plants. That was cool. I thought that was awesome.
All right, let's start the class. A couple of reminders. There's a homework that's in progress, and I hope you're, doing or close to done with it. We'll be looking at one part of this, or at least today's lecture will be useful for one part of the homework, which is question 2, which talks about the EM algorithm. I know that some of you already jumped ahead and gone through the slides and worked it out. Good for you. My fond hope is that we will at least cover enough that you should be able to do the homework question completely. If not, keep an eye out for announcements. There may be an extension of a couple of days so that you get time for the homework. Which means if there is an announcement, that means the homework will be due on the absolute last day of the semester. If not, it's the 8th. We'll see how today goes. And that doesn't mean this is an incentive for you to basically interrupt the class. But my TS and I will discuss this tomorrow, and we'll make a call on this. And as I mentioned, there's an exam on the 16th for 2 hours, and it will cover everything that we did from learning theory. Basically, everything that was not covered in the midterm will be tested. And I guess that's all the announcements I have. Any questions about any of these things?
Just one question about Naïve.
Sure.
So is it somewhat analogous to, so we have 2 steps. We have the prediction rule for predicting which label is the highest probability.
Prior.
And we have the maximum likelihood test where we search over all the hypotheses. So can we think of the search over all hypotheses as a training method?
Yes, this training by definition is search over hypothesis. Prediction by definition is search over outcomes. So maximum likelihood prediction is search over all outcomes. Maximum likelihood learning is search over all hypotheses. In fact, one interesting way of thinking about a lot of learning algorithms is it's basically, as I mentioned probably early on in the semester, learning is just search. One interesting way of thinking about learning and prediction is both learning and prediction are search. Learning is search for the highest, some definition of best, the best hypothesis. Prediction is search for the best label, right? I mean, the best label according to a particular hypothesis. It so happens that for Naïve Bayes, both learning and prediction, both these search problems, the definition of best is maximum a posteriori. Okay, so we have a fun lecture today. Today's lecture will start, certainly the last new topic that we'll cover in the semester. The plan is today and on Tuesday we'll continue with this idea of learning when you don't have fully labeled data, and on the next Thursday, that's the last lecture of the class, I was debating between doing a review of the semester for the exam, or talking about how to apply all these things that we saw on practical problems. Meaning you finish the semester, you go out and you get, say, a job at Google. How do you use any of these ideas? And I think the latter is more important because, the exam is just an exam. Google is going to control my email. So I'm favoring the survey, or actually the practical thing. So there may be some other avenues for reviews that we are still discussing. So I'll let you know about that next week. So in the last lecture, we spoke about logistic regression. We saw the logistic regression classifier, and after some massaging of the algebra, we found that learning this classifier is simply minimizing this thing. Maximum a posteriori learning of the logistic regression classifier is equivalent to finding a weight vector that minimizes this quantity. And if you don't remember this, I encourage you to go over the slides, and it's basically just algebra, so I'm not going to do it again. The main message here is this must look very familiar, and it's basically the same sort of function that we saw for support vector machines, where we had this loss term and a regularizer, and in support vector universe, the regularizer was motivated by this idea that minimizing the norm of W maximizes the margin. We like big margins, so let's add that into the objective. In the logistic regression view of life, the regularizer shows up because minimizing this quantity, if you remember, I'm not going to go over the derivation, but minimizing this quantity, or in this case maximizing the negative of this quantity, actually maximizes it pushes the weight vector, the probability towards the origin, actually pushes W towards 0. When W is all 0, look at the prior is the top line. When W is all 0, it's the highest probable. Because it's a Gaussian centered at the origin, which means that in the absence of any information, the most probable weight vector is the origin, because that's the one that's most uninformative. Because if all your weights are 0, you're practically tossing a coin. So in the absence of any information, move it to the least committed weight vector. It's just another perspective on this. It turns out the math of it works out the same. It amounts to adding a regularizer that is the norm of the weight vector. This is the Bayesian interpretation of the same object. Okay? And the good news is we know how to solve this problem, and I'm not even going to cover this in the class because I have done stochastic gradient descent way too many times, enough that I'm sure some of you are bored. So the good news is that you're doing it for the homework, or have done it for the homework. So you'll be deriving, defining the stochastic gradient descent algorithm for this objective, and should be a minor tweak. All you have to do is, the only tricky part is you need to know how to take the derivative of this log of 1 plus e power blah blah blah. SGD is not the only algorithm that's used here. In practice, many other optimization algorithms are used. One thing that shows up a lot, actually, one thing that shows up, and it used to show up very frequently about 10 years ago, was this algorithm called LBFGS. It's kind of losing favor these days, partly because it's just a pain to implement, whereas SGD is, I can give it as a homework and not worry about frightening you. So, in general, at least for logistic regression, you can implement stochastic gradient descent. So, are there any questions about this? Anything on this area? Yes.
So we're doing the MLE, right? Or are we doing maximum posteriori?
This is maximum a posteriori because ML, the first term here, comes from the likelihood. If you're doing just MLE, you get this thing inside the box. Only the loss. The maximum a posteriori, look at where each of these terms come from. The first term comes from the likelihood. The second term comes from the prior. If you have a prior and a likelihood, you're doing map. So map learning for logistic regression is exactly the same as minimizing the regularized logistic loss. So if there are no more questions about this, let's go back, let's tie this all up with what we saw for the large part of the second half of the semester, which is loss minimization. So this is, again, just to remind you, a general recipe for writing down learning algorithms, where you have some examples, they are drawn from some distribution, we don't know and we don't care. and there is some hidden function that we want to mimic, and so we are going to search over a space of hypotheses, and the way we'll frame learning is we'll define this function called loss, L. L penalizes functions, hypotheses that are bad. So a natural way of learning is to just find a hypothesis that has the minimum loss. So this is the most, or one of the most normal, natural ways of defining learning. What we care about is minimizing expected loss, because we don't really want to minimize loss on the training set. We want to minimize loss on future examples. We care about minimizing expected loss, but the problem is this distribution D that governs the data is unknown, unknowable sometimes. Instead, what we'll do is we'll minimize the empirical loss on the training set. Count or add up all the penalties that your function hypothesis pays for every training example and find the hypothesis that pays the lowest cost. We've seen this many times, and the problem with just this version of the story is that it's prone to overfitting. We need some way of guiding our functions towards simplicity, guiding our search towards simpler hypotheses. And that is the job of a regularizer, which penalizes complexity. And there are many ways of thinking about regularizers. Regularizers penalize complexity. For SVMs, regularize, penalize, or maximize the margin. For logistic regression, the same regularizer acts as a Gaussian prior. Just different ways of saying the same thing. So what we have is, for many linear classifiers, we're trying to minimize the sum of two quantities, the sum of a loss term, an empirical loss, plus the regularizer, the norm of the weight vector. And there's some scaling factor that controls how much you want overfit versus underfit. Now, of course, the question is, what's the loss that we care about minimizing? One natural loss to minimize is whatever function, whatever your program will be evaluated on. If your program cares about maximizing, say, the number of positive predictions, the number of correct predictions among positives, only the positive class, then maybe that's what you should optimize. In most of the time, we care about maximizing accuracy. And accuracy is 1 minus error, and that is called the 0-1 loss. The 0-1 loss is simply this function that takes two labels, the true label y and the predicted label y prime, and it takes away a point if they are not equal. If they are equal, you don't lose anything. This is, for linear classifiers, this is equivalent to saying that basically we are checking, is there a mistake? And we've seen that mistakes are the same as saying y times the dot product is less than 0. So you lose a point, or not you, your classifier loses a point if y times the w transpose x is less than 0. Otherwise, it doesn't lose anything. This is the object that we would like to minimize. Unfortunately, this is minimizing this quantity is intractable, so we need to invent surrogates. All through the semester, we've been inventing surrogates, actually, it turns out. We looked at the perceptron algorithm. Actually, the perceptron algorithm is minimizing the perceptron loss. SVM minimizes the hinge loss. The AdaBoost minimizes a loss function called exponential loss. The logistic regression, even though we came at it through this complicated, well, not complicated, but long, circuitous, maximum a posteriori line of thinking, and we introduced this sigmoid function and all those things, it turns out it's minimizing the logistic loss. All of these are surrogates for this one loss function that we truly care about, which is the 0-1 loss. And we've seen all of this before. I just wanted to bring this up to put this in perspective. This is just a picture that I was able to draw, so I thought I should put it on a slide. We care about minimizing the 0-1 loss. And the x-axis here is y times w transpose x. Meaning, if y and w transpose x have opposite signs, here, you lose a point. If they have the same sign on this side, you don't lose a point. That's your 0, 1 loss. Hinge loss says, not only do you, if y times w transpose x is greater than 1, you don't lose a point. Between 0 and 1, y times y and w transpose x have the same sign, but you still pay a penalty because you are within the margin. So it likes to push find weight vectors so that all points are on this side. And you pay greater penalties as you make larger mistakes. And logistic regression is a similar sort of a thing. Okay, let's just go according to what I have. Perceptron, on the other hand, says every mistake and only mistakes pay a penalty. There's no notion of a margin here. Add boost minimizes the exponential loss, and the logistic regression is just another one. So, and there are other loss functions also. If you feel that there will, say for example, you have some application where you know something about your problem, something that only you can capture into a mathematical formulation, then you may want to invent a new loss function, but I would recommend, try something that exists first. Was there a question? Yes.
Is the margin perceptron still using the perceptron law?
Right, the margin perceptron actually just moves this curve to some place here.
So then what's the difference between that and SVM?
Excellent question. What's the difference between a perceptron and an SVM? With respect to the loss?
We still pay a mistake if we're, on SVM, we still pay a mistake even if we get it right if we're within the margin.
Right, and the margin perceptron does the same thing. But with respect to the entire objective, what's missing in perceptron?
Regularizer?
The regularizer. The perceptron is not regularized. So we still don't get the VC guarantee, which is why we need average perceptron. Averaging is a technique to inject generalization into perceptron. SVM typically does not benefit from averaging because it has a regularizer. So generalization is baked in. Yes?
Just a question. I'm kind of hard to understand why the 0, 1 loss, because that's like the ideal loss.
Yeah.
If we could, we
Right,
would
right.
minimize that one. Why is it so hard to?
It's anti-hard to optimize.
Is it just because it's not continuous? Is that
Not just that, it's not continuous, it's not convex. So if you look at all of these are convex functions except the 0, 1 loss, which is not convex in this region. The way to test that is to take a point here and take a point, take 0, draw a line, the function's above it. A convex function should always lie below the secant. Yes?
You said something just a moment ago about a guarantee with the SVM
Right.
and VC dimension. What did you say?
So think about what the SVM has. The SVM has a regularizer and the hinge loss. The job of the regularizer minimizing the norm of the weight vector maximizes the margin. Maximizing the margin gives us lower VC dimension. Lower VC dimension gives better generalization. So minimizing the norm of the weight vector gives better generalization. Perceptron has no such thing, which is why we have averaging.
So, looking at how quickly these functions are, well, I guess decreasing, going from left to right, but increasing from right to left. It looks like Ada Boost, has the biggest penalties for being wrong.
Right.
Logistic regression having the smallest penalties.
Yeah, I've zoomed in quite a bit here. If I zoom this out, logistic regression and SVM kind of catch up.
Okay.
Yeah.
Is there any penalty associated with having very small penalties for errors?
So that's actually a good question and something that cannot be answered in general. It depends on your application. I can tell you from my experience that very often I have had a hard time finding a difference between a classifier that's trained with logistic regression and one that's SVM. Actually, to be honest, even logistic regression, SVM, or average perceptron. If you a well-tuned version of each of these, meaning you do cross-validation, find the best hyperparameters, they all behave roughly the same. Because this is the zoomed-in version. When you zoom out, they are all okay.
Shouldn't the part of it depend on the distribution of your training set data points?
Right, which we don't ever know, right? We never have access to that distribution because It's an unknown but fixed distribution. Which is why I said, it depends on your specific task. Was there another? Okay, you first.
Are there any loss functions that their penalty slows down as it becomes more and more wrong, so as to not care about outliers?
Right, you have to be careful that you don't make it not convex.
Yeah, but still convex, but the penalty kept getting less and less over the same, given a certain amount of error.
So wait, let me try to understand this. You are looking for something that may, if I just draw something, so let's say it has very low penalty here, it goes up and then it goes down.
Yeah.
But this region is not convex.
Oh. Yeah.
So you have to be careful not to.
Yeah, that makes sense. So it actually has to keep getting worse.
It has to be in fact, all of these are actually monotone functions.
Okay.
So I saw many hands, so yes.
The idea of kernel is, of course,
Oh, the kernel is an orthogonal idea because the kernel says, kernel is inside this quantity here, right? Instead of W transpose X, you are getting a dot product in a larger thing. So you are measuring dot products in larger space. You have kernel perceptron, you can, of course, you have kernel SVMs. Anytime, so for logistic regression, I have to think about this, but I suspect it can be done. But kernels are talking about dot products in higher dimensional spaces. So anytime your final weight vector looks like the sum of input points, you can make it a kernel. So I think for logistic regression it's doable, but actually the math should be worked out.
Kernels are simply concerned with feature transformation.
Yes, yes. And as I realized in the deep learning class yesterday, another phrase that is more commonly used than feature transformation is actually a lifting map. You have your features in some space, you lift it to another space. It's the same thing as a feature transformation. So yes, kernels are concerned with that. Representation. Kernels are concerned with representation. Are there other? Yes.
So going back, there was a question that was asked about a potential loss function that minimizes the error outlying. I just want to know, is there a way you can do something similar to the 0 and 1, but just instead of having that discontinuous cut in the middle, could you just have it be a linear segment between?
So let me draw something and you can tell me whether that's what you're thinking of. So let's use a different color here. Nothing's going to be visible. Let's use red. So you want something that's 0 here, and then let's say it goes up linearly, and then it becomes this way.
Yes,
This is not convex here.
that's right.
You have to be careful to keep it convex.
Thank you.
I'm not saying that convexity is necessarily the only thing to worry about, because in fact one of the big things that's happened in the last decade is, stop worrying about convexity and just accepting, or non-convexity and just accepting it. And that's what basically works for multi-layer perceptrons and deep learning and such things. I'm not saying it's not the work, I'm not saying it's bad, but it does not have all these nice properties that one might want to teach in a first machine learning class. But you should try it out.
In terms of convergence, right?
Yes, exactly. Or guarantee that you will get to the absolute minimum, because if it's not convex, we only know how to get to local minimum. Okay, just to continue this, from this perspective, actually it turns out logistic regression is 4 things. It's a classifier that has been trained to predict the probability that the label is 1. All the other classifiers that we saw predicted the label, not the probability that the label is 1. Logistic regression is a discriminative version of the naive Bayes classifier, because we just saw that in the last class. Their prediction rule is identical. Logistic regression is a discriminative classifier that can be trained with maximum posteriority or maximum likelihood, and it's a discriminative classifier that minimizes the regularized logistic loss. Very often the regularization part is skipped, especially in older literature, but my general advice is don't skip the regularizer, because that does that. So on one hand, it's this loss minimizing object. On the other hand, it's basically maximizing the likelihood. They are the same thing. I mean, the logistic regression classifier is something that does both of these things. And as a side effect, it also gives you a probability if you want. And that's one of the reasons why it's like very widely used, because people like, in some applications, you may want to use the probability rather than the actual label. And we'll see one use case of when the probability becomes useful actually right now. Are there questions? Once, twice, 2.5. Okay. So we're going to switch gears now. And we're going to go to something completely different. Learning when you do not have any labeled data. So for pretty much the entire semester, we've been looking at supervised learning. Well, I'm looking at it. For the entire semester, we've been looking at supervised learning. We've been looking at the setting where every training example comes with a label. So you get these pairs, x, y. X is a vector, y is plus or minus 1. And given this, at this point, I hope, you should know how to train classifiers. And not only should you know how to train classifiers, you should have some way of justifying your choice for a learning algorithm. Why you pick this feature vector over the other, why you pick a decision tree or a nearest neighbor or logistic regression or whatever. What if, instead of getting these pairs of x, y, someone only gave you these labels were hidden. I only give you input vectors and don't give you any labels. Is learning possible? Or if that seems too extreme, what if I give you a very small number of labeled examples, maybe 10 examples that have labels, and 100 million examples of just input points? The category where you get a few labeled examples, the class of problems where you get few labeled examples and tons of unlabeled examples is called semi-supervised learning. And when you don't have any labels, it's called unsupervised learning. These are technical terms, but their names are obvious. I mean, there's no supervision or there's little supervision. So this chapter of the class is going to talk about can we solve this problem? How do you do it? And we'll look at probably one of the more famous algorithms, probably the first algorithm that most people think of when you think of unsupervised learning, that's called expectation maximization, EM. And through EM, we'll also look at, most likely in the next lecture, we'll see how there's this popular clustering algorithm called k-means, and some of you I'm sure have seen or used k-means at some point. Turns out k-means is actually a special case of EM. So let's look at semi-supervised learning or unsupervised learning. Apparently we live in the land of big data. There's more data than we can manage and all that good stuff. But actually I think we live in the land of big unlabeled data. Getting labeled examples is probably is much harder than just getting examples. And I know from talking to you that some of you are already facing this problem in your projects. I mean, you don't have example data. You want to solve a problem. You want to decide when a spacecraft will explode, but nobody's given you 100,000 examples of spacecrafts and explosions. Just some examples. A common thing that shows up in bioinformatics or biology, if you have labeled examples for, say, any biological data sets like genome stuff, not every, but very often, getting the label involves running some experiments in the wet lab that costs several $1,000s. So every data point is expensive. My favorite application is natural language, where if you want to annotate semantics of text, we need to hire a bunch of linguists, put them in a room for a few years, and we'll get some labeled data and a lot of disagreement. If computer vision is a similar thing. if you want to annotate videos or images and such things, either you have to pay people a lot of money and run a large annotation task, or you have to come up with these kind of cute games that Google does when they trick you into providing labels by making you play games. So in any case, label data is expensive and really hard to get, and very often requires experts. So for example, for the language data, we need to hire PhDs in linguistics to annotate data. On the other hand, unlabeled data is everywhere. And the key question in unsupervised learning is, can we learn classifiers, for example, without any unlabeled data? So, just to kind of set the stage, say I give you some points. How do you label them? Let's say your labels are red and blue. How do you label them? Which points are red, which points are blue?
The left cluster is red, the right cluster is blue.
Excellent answer. That's one of them. Okay? The reverse. Right? So, first lesson, when you're learning without labeled data, sometimes you can get classifiers only up to symmetry. There's no way of knowing. If I tell you there are two clusters here, two groups, and I give you names, there's no way of knowing which group belongs to what name without annotation. But how many people agree that these are okay labels? One of these two. More people than have ever raised their hands in this class. So that's an overwhelming majority. But why not this one? This is linearly separable. I don't know how you assume that these nice clusterings of examples are the ones that matter. It turns out, without labeled data, you can't get anywhere unless you make further assumptions. For example, unless you make assumptions about the regularity of points. The assumption that was in play here is that the separating hyperplane should go through regions of the space that are not dense. There's an implicit assumption that all of you seem to have agreed on without me ever prodding this, unless some of you are actually looking at the slides, but it doesn't matter. Right? So, two important points. When you're doing unlabeled, unsupervised learning, you may learn your parameters only up to symmetry. And second, when you're doing unsupervised learning, you need some modeling assumptions. You need to assume something about how your data is laid out. Semi-supervised learning, on the other hand, is actually kind of fun. Say you have a million labeled examples, or in this case about 20, and you have, million unlabeled examples and maybe 2 labeled examples. Just those 2 labeled examples may help you break the symmetry. Right? It's like you have 2 puddles of water, putting a drop of ink in one of them just colors the entire puddle. So semi-supervised learning lets you break symmetries because those few labeled examples tell you which cluster should be given what name. So let's take an example. All of you know Naïve at this point. Say we have a Naïve classifier. There are 4 features and there's a label 1. Say you had training data and you know how to, at this point, you know how to estimate these parameters. The prior, that is saying what's the probability that the label is 1 in the absence of any feature, and the likelihoods for each feature, the class conditional likelihood. The probability that the label is 1 when, the probability that the jth feature is 1 when the label is 1, and the probability that the jth feature is 1 when the label is 0. If you knew these numbers, A, B and P, then you can just predict labels. You can go out and label tons of data, right? If you knew the parameters, if you have a classifier, you can go and label examples. So, say you had a small number of training examples, and you learned these parameters, these classifiers, you can go to your big bucket of unlabeled data and label each one of them. That's basically just running your classifier. And we know how to train these parameters because we've seen this before. The prior, which is the probability that the class label is 1, is simply the fraction of examples where the class label is 1. The probability that the label is 1, the jth feature is 1 when the label is 1 is simply count how many times the jth feature is 1 for examples that have label 1 divided by the number of examples that have a label 1 and so on. We've seen this. So let's kind of build up a technique that can use what we know to and yet exploit unlabeled data. So let's start with some simple case. Say you have 10 examples. Based on 10 examples, you've learned a classifier. The probability that the label is 1, the prior, is half, let's say, which means the probability that it's 0 is also half. You also learn the likelihoods for every label. The probability, so just to remind you, say this cell here says what is the probability that the second feature is 1 if the label is 0. So let's say we've used 10 training examples to get these numbers. And now we have an unlabeled example, 1, 0, 0, 0. I can predict this quantity. The naive Bayes assumption says the probability that the label is of a label given the features is simply the product of the prior and all the likelihoods. We have all these numbers. We know the value of x1, which is this, right? So we can just plug in these numbers. So I did that. So probability that y is 1 given that the input is 1, 0, 0, 0 is proportional to that quantity, 12 over 256. Probability that it's 0 for the same example is proportional to 3 over 256, which means probability that the label is 1 for this example is 12 over 15, that's 4/5, and the other one is 1/5. This is just computing posterior probabilities using naive Bayes. I have a naive Bayes classifier, I've just computed the posterior probabilities of the labels. Right? Questions before we go ahead?
Where does 15 come from?
Where does 15 come from? So, this quantity is the same as this. Right? And this thing is the same as this. I know these two numbers should add up to 1. I know that they are proportional. This one is 12 over 256, this is 3 over 256. They should add up to 1, which means probability of y equals 1 given x plus probability of y equals 0 given x should be equal to 1. I know that this is proportional to 12 over 256. This is proportional to 3 over 256. And there's a proportion which they have to add to 1, so the sum of them is 15 over 256. So the denominator is just 15. Other questions? So what we have here is, if I had 10 training examples and I was able to compute the parameters of your naive Bayes classifier, then for this particular new example, that remember it did not have the ground truth label, or you'll see the phrase gold label also. It does not have the gold label. So for that new example, I'm able to compute the probability that it belongs to a certain class. The probability it belongs to class 1 is 12/15th, and the probability it belongs to class 0 is the rest. So the question is, what can you do with it? Can you do anything? Does this give you any new information?
It seems likely that it should be labeled 1.
Seems likely it should be labeled 1. So what can you do with that? Can you improve your classifier? If I tell you, using that observation. So you still have your 10 training examples.
You can add it to the examples.
So you get 11 training examples, right? So you get more data, more labeled data, and recalculate the probabilities. So one option is, according to this model, according to the current model, your classifier thinks that this example should be labeled 1. So let me just label it 1. So I get a new labeled example. Somehow I have hallucinated a labeled example. Let me add it to my training set and recompute the probabilities. You could play some games that says, I'm going to only use those examples where my classifier is really, really confident. Meaning the probability of y equals 1 is more than, say, 99%. Then almost certainly it's going to be 1, so might as well use it as a labeled example. Can you do something else? Yes?
You can make them 2 examples and weight them with respect to the probabilities.
Exactly. Or another way of saying the same thing is the model does not predict the label. It predicts fractional labels. This example is, remember that for training a Naïve-based classifier, all we have to do is count. We are counting how many times this feature occurred with this label and such things. Counting is just iterating over these things and adding 1 to the counter, right? Who said that you should add 1 to the counter? I can add a fraction. So instead of adding full counts, I can add fractional counts. So we can say that this example has a label 1, or actually it is both 1 and 0. It's 1 12/15th of the time and 0 3/15th of the time. Right? This idea of fractional counts is kind of, it's important when we are talking about EM. So are there questions? Okay, so you have one new example. Alright, so just to summarize, we have two approaches of using unlabeled, that one extra example that we had. I can use my current estimate of the probabilities. Doesn't have to be probabilities. I mean, the example I had was naive Bayes. I can use my current classifier to label the example as 1 or 0, treat it as a new labeled example and give it back to my learning algorithm and keep it rated. Or I could say that this example is both 1 and 0. It's like Heisenberg's cat. Anyway, it's both 1 and 0, and it's in both these states, and you use this to somehow improve your model. In the naive Bayes universe, it's actually fairly simple to use it because all you're doing is counting, and instead of counting with integers, you count with fractions. You add up what fraction of the time it is 1 and what fraction of the time it's 0. And you could keep doing this. So you get a current model, you have your 10 training examples, those have fixed labels because some biology experiment was conducted and that particular example was unequivocally plus or minus. There is no doubt that that example has the correct label. So you have 10 labeled examples that you can always rely on, and you have a million unlabeled examples. What you do is you use the 10 labeled examples, go label all the million of them, either with entire labels or fractional labels, re-estimate your probabilities. Now you get a new model. Go back to the data again, use your new model to relabel the data, re-estimate your probabilities, and keep going. You can do this forever if you want. Right? This is a strategy for semi-supervised learning. You start off with your labeled data and iteratively improve your classifier by labeling the unlabeled data. So we had supervised data. What can you do if you don't have any supervised data? Or instead of 10 labeled examples, what if you have only 0 labeled examples? What can you do?
First example comes in, you can just randomly assign it a label.
Examples are not coming in, you just have a bucket of examples. But that's the. Go on.
I was just going to say that people have a bucket, give it away.
Yeah, exactly. Or what did we do with the 10 labeled examples? We learned an initial model. Right? We can do the same thing. We learn an initial model using 0 labeled examples. Just come up, hallucinate a model, pick a random set of parameters, because if you have 10 examples, you write some function, you write some code that does something. 0 is also a number, it should execute for 0. All you do is just start with random. You start with a random model and then continue the same thing that we did before. Iterate. Start with a random model, use that to label some examples. Now you have labeled examples, learn the model, go back, iterate. Questions?
I guess you have to assume.
Yes, first you, because you raised your hand.
Does it convert?
That's a good question. Hold on to that thought. Well, actually, this is not a suspense novel. Yes, it converges, but only to local minimum.
I guess you have to assume how many labels you have.
You have to assume how many labels you have.
Yeah.
Because if I give you a set of points and say learn, then let's say I give you a data set. I just give you a bucket of points and I tell you learn. Your first question would be learn what? Right? And that one of the things that defines what is the number of labels. Yes?
I'm still confused, how do we update the labels to each iteration? Because we never see the labels, so how do we?
We never see the labels. So one way of thinking about this is, think of who gave you the labeled data. There was this expert, this biologist who did wet lab experiments, right? The oracle function F. Instead of using the oracle function, what if you used your classifier as the oracle on the unlabeled data?
Okay, but how do we know that the classifier is right? Because we're making up an hypothesis to make predictions, but we don't know the initial.
Yes.
We're building up a story to make more stories.
Yes, exactly. You're building castles in the air and it might fail, but the good news is that with not very strong assumptions, this will not fail only up to symmetry. You know that data set that I had with those two clusters? You will get one of those two classifiers. It will fail either it will fail catastrophically, meaning it labels every point incorrectly because it's symmetric, or it gets it correct. Were there other questions?
But it will look for the least dense area to
You need more assumptions for that to happen, but that does. I mean, you need a modeling assumption for that. Yes.
So would you want to do unsupervised learning during like a testing?
You could. In fact, that's a good idea. You could. There's no reason not to, because at test time you have you don't get any, you don't lose any points for not using that data. You don't lose points for using that data because there is no label. You could, but it is not always done, partly because every learning step becomes more complicated. That said, there is a variant of this kind of supervised, unsupervised kind of learning called transductive learning, where you're given a bunch of labeled examples and you're also told upfront, these are the examples on which you will be evaluated, and I'm not going to give you the labels. And transductive learning tries to find a classifier that best labels the test sets. That makes some close word assumptions, but yeah. So the interesting thing is this sort of what might seem like an intuitive or what might seem like a rather radical idea is a very basic version of the expectation maximization algorithm, or the EM algorithm. So let's get started with the EM algorithm. So first of all, when I will keep saying EM algorithm, but actually EM is not one algorithm, it's a recipe for generating algorithms. Okay? It's a meta algorithm that is used for estimating probabilistic models when you do not have labels. And so given that we saw discriminative and generative models, EM is particularly suited for generative models. And remember, for generative models, we have to assume a generative story. We need to come up with a model of how we believe the data is generated. What probabilistic? First, the label is drawn from some process, and then based on the label, the features are generated, and something like that. And very often, the quality of the classifier that you get is very strongly tied to the validity of those generative assumptions that you make, which should not be a shock, because if you make incorrect assumptions, then you're not going to get a good classifier. That's pretty much what it is. The nice thing about the EM algorithm is that it comes with rather strong guarantees of the form that at the end of the iterative process, and it's a specific iterative process, at the end of the iterative process, you will get the local maximum of the likelihood function. It turns out when we try to write the objective function for maximum likelihood estimation, when you do not have fully labeled data, that function, the maximum likelihood objective, tends to be non-convex. So this is the first time, probably the only time in this class, we are talking about non-convex optimization, and the general lesson in non-convex optimization is all bets are off. The best hope that we have is we get to the local maximum, or in this case it's local, we are talking about concave local maximum. Okay? So I'm going to introduce EM through a series of examples. Mostly this is like a puzzle. So say I have 3 coins, 0, 1 and 2. The biases of these coins are alpha, P and Q. Coin 0, the probability that 0 gets to heads is alpha, and P and Q are for 1 and 2. Let's take let's think of various scenarios that we can have with these 3 coins. Say I pick 1 or 2, I don't know which one or 2. Toss it 4 times. And I get this label, this observation, 3 heads and a tail. So now the question is, suppose I knew what are the biases of the coins, alpha, P and Q. Can you tell me which coin was tossed? Okay, which coin is more likely to be tossed? How do you do it?
Whichever is closest to 3/4.
Oh, is that right? But what does that mean, whichever is closer to 3/4?
You assume that 3 out of 4 times came up heads. So whichever coin has a bias that says it's closest to 3 out of 4 times.
Okay, but can you formalize that argument using words like maximum likelihood or maximum posteriority?
Let me get back to you.
I can ask the following question. The object that I care about is the probability that the coin was 1 or 2 given the observation. The posterior probability of the coin given the observation. Right? And I know by Bayes' rule that this is proportional to the likelihood, assuming that the choice of 1 and 2 is even. So the posterior probability is proportional to 1 and 2. And I know also the value of P and Q. So the posterior probability of coin 1 is proportional to P cubed 1 minus P. The posterior probability of coin 2 is proportional to Q cubed 1 minus Q. I know these values, so I can just compute them. And whichever one is higher is more likely to be tossed. Right? Questions?
What happens if we don't know P and Q, we don't have those initial probabilities?
Right. In this game, we know P and Q.
Okay.
But that's the next game. But just a summary of the lesson so far, if we knew the probabilities, you can figure out which coin was tossed just by looking at the observations. By the way, this is very similar to part 1 of the EM question, or part 1 or part 2, one of these parts. So let's say that we play another game. First, we have 3 coins. So far I've been only using 2. Say I toss the first coin, coin 0. If it is heads, then I pick coin 1 and toss it 4 times. If it is tails, then I pick coin 2 and toss it 4 times. And I do this process 4 times. So each time the blue letter here is what was the value of coin 0 and then the subsequent tosses. So for example, in this case, coin 0 gave me a head, which means I need to pick coin 1. So these are all coming out of coin 1. Here coin 0 gave me a tails, which means these are all coming out of coin 2. Now, if I give you this observation, can you estimate the values of alpha, p and q? How?
You just count?
You just count. But just to make this into, just to make this slightly more complicated, I'm going to give you a generative story for this. Generative story is, first coin 0 is tossed. Meaning this random variable is observed because each coin is a random variable. So that coin, you take a sample from that distribution. And based on that, the other 4 coins the other 4 observations are made independently. So this is independent of this if I know that this is the coin 0 was heads because coin 1 was lost 4 times. But as many of you said, the value of this alpha, p and q can just be obtained by counting. There are 4 tosses of coin 0. 3 out of those 4 are heads, so the alpha should be 3/4. For coin 1 it turns out is tossed 8 times and 12 times and 8 of them are heads, which means p is also 3/4 and q is a half. Right? So if I knew what the coins were and if I had, in this case, fully labeled data. By the way, what we have here is we've just trained a Naïve Bayes classifier. If I have fully labeled data, here the label is the blue stuff, the coin 0's value. If I have fully labeled data, then getting the values of these probabilities is easy. You just count and take fractions. Okay, so we've done the easy stuff. Let's get to unlabeled data. Say I toss coin 0 first. I do the same thing as before. I toss coin 0 first. Then if it's heads, I toss coin 1. If it's tails, I toss coin 2. And then I don't tell you, and then I just show you what was the value of the tosses produced by 1 or 2. I don't tell you which coins produced I don't tell you the value of the first toss. Okay? You see the connection to unsupervised learning. I don't give you the label. I don't tell you which class each of these examples came from. So now our goal is to somehow estimate the value of alpha, p and q. Good news and bad news. The bad news is this problem cannot be solved. There's no analytical solution. In the previous case, there was an analytical solution. You do maximum likelihood estimation and all that stuff, and it turns out the probabilities can just be estimated by counting. In this case, there's no analytical solution. So you can't do maximum likelihood learning on paper. So you need to actually invent an algorithm that does some estimation. The good news is we have such algorithms. So before going ahead, let's see what we know. Scenario 1 was the case when you have, when you know the values of p and q, and I'm asking you what's the label, what's the most likely value of, what's the most likely coin that tossed it. In other words, what was the most likely label? What was the most likely toss of coin 0? If I knew the observation, if I knew the biases of the coins, I can estimate the missing labels. That's basically like saying if I have a classifier, I can label an example. Scenario 2 says, if you knew which coin produced the data points, or which coin produced the data points, then you can compute all the, what do you call it, you can compute all the probabilities. So now we need to somehow use these two ideas to solve scenario 3, where the value of the coin 0's toss is hidden from us. One way is very analogous to what we saw before. You guess the probability. Just start with a guess that for each coin, you guess whether it came from coin 1 or 2 for each sequence of observations. And then you keep iterating. Now, you have a way of getting a label for every value of every observation, which is this 4 tosses. You have a way of estimating, based on your current guess of these probabilities, you can estimate, did this come from coin 0 or coin 1? Sorry, coin 1 or coin 2. But once you get that, you have fully labeled data. And you have fully labeled data, you can use maximum likelihood to estimate the biases. But now you have the biases, meaning you have all the probabilities that you care about. You can use the probabilities to re-estimate which coin tossed the produced the sequence, and you keep looping. And the theory says this will converge to the local minimum of the overall likelihood function. We haven't seen which likelihood function, but we'll see that in a minute. But before getting into the details, are there questions about this general scheme? Yes.
So when you said that there was no analytical solution, you meant that there's no formula that will get it?
Yes.
But there is a solution?
There is an algorithmic solution. You have to execute this, and if at convergence, this will get to the local maximum. But there is no formula. Like Naïve Bayes. I mean, in Naïve Bayes, there was an analytical solution. In this step here, for example, we have an analytical solution because it's just counting. Other questions? Right, so now let's start talking about EM, or maximum likelihood estimation with missing labels. Generally, maximum likelihood estimation is to find the parameters that maximize the likelihood, or maximize the log likelihood. I'll use the notation LL for log likelihood. You'll see that a lot in papers, and that's simply the log probability of the data, training data. And we know that each training example is independent, so it's just the sum of all the log probabilities. And we have been doing this for a while, so I'm not going to label this point. But to connect this to what we saw before, in this coin game that we are playing, the parameters are the biases of the coins, the alpha, p, and the q. Each example, xi, is that ith string, the string of 4 coin tosses. I don't know whether it was coin 1 or 2, but I do know that these are the 4 observations. And just to make the analogy complete, I'm going to refer for every observation, I'm going to refer to the value of its coin 0 toss that I have hidden from you as yi. Okay? So we care about maximizing the likelihood of the data, the log likelihood of the data, maximizing, finding those values of the parameters, finding those values of alpha, p, and q that maximize the likelihood of the data, which is just the same as saying, find the value of alpha, p, and q that maximizes this summation. Remember that when by example, I mean just this xi. Example I is just the observation that we have. We want to find the parameters that maximize the likelihood of the observation. But all we know is some way of calculating the probability of the pair xy. You know, how we do with Naïve. So we know how to calculate P of xi, comma yi. This is a vector. Whereas this given say alpha, p and q, we know how to calculate that. But this thing here is P of we have a expression that lets us compute this quantity, but we care about this quantity here. How do I reconcile this? What are the values of yi in our coin example? What are the different values that yi can take? Heads or tails. It's the corresponding value of coin 0 toss, which we don't see. Okay? So now, how do I, what's the expression for this quantity here? Can I make it somehow, can I do something? The law of total probability. This quantity is simply probability of x I and heads given alpha pq plus probability of x I comma tails alpha pq. Right? So this process is called marginalization. You have these hidden variables that you are not aware of, the yi, and you marginalize it out, you sum it out. You just sum over all the yi's. Questions? It's going to get rather hairy very quickly, so please stop me. Okay, let's move on. Let's just plug it in. We know that the probability of the example given the parameters is this, you can marginalize it and write it in terms of this total probability. So let's just plug it in. So the log likelihood of the data that we care about maximizing is this sum over each example log of sum over each label. So that this is the sum over each example log of sum over each label, this quantity. Turns out this objective, the one that we want to maximize, this is the one that's not convex. This function is not convex in alpha pq because it's this summation inside the log, and I'm not going to, you can take my word for it for now. So we want to maximize this, and let's try to, instead of maximizing this function, let's try to find a different function. Let's try to approximate this. You know, if you, this is like the game that I probably mentioned this a few times in office hours. If you lose a ring under the tree where it's dark, you can't search for it there, so you search under the street light because you can actually look. So that's what we are doing. We want to solve this problem because it gives us the maximum likelihood estimate. Instead, we are going to construct another problem which is related to this and try to solve that. There is a mechanical construction here, and this is basically the heart of EM. Say I have another function q. Let's say q is well behaved, it doesn't go to infinities or zeros. In fact, let's say q is a probability distribution. I can multiply and divide the term inside the summation by q. Right? I've done nothing here. Just multiplied and divided by q. Right? And I'm assuming that q is some probability distribution. It's true for any probability distribution, but notice the quantity inside this box here. It is sum over all y, q of y times something. I don't care what it is. It's q. Instead of y, I've used z at the bottom, sum over all z, q of z times something. That's literally the definition of expectation. So it turns out what we have here is an expectation according to this distribution Q, an expectation of what? Expectation of this ratio, P of xy divided by Q. So let's just replace it with the expectation. So what we have here is the sum over each example of the log of the expectation of, there are so many of, sum of log of expectation of this ratio, and the expectation according to what distribution? Some distribution Q, any distribution Q. Of course, we will not use any distribution Q, we will fix one in a bit, but let's stare at this function a little now. Now, so far I have done nothing. From here to here to here is just a rewrite. It's just I introduced a Q and just rewrote it as expectation. But now we can actually use some interesting properties of this function log to build the approximation. And the property that we are going to use is called Jensen's inequality. How many people have seen Jensen's inequality before? 2 people are raising their hands, so I'm going to assume 5. So Jensen's inequality is a property of any convex function. It simply says, and this is actually not terribly hard to prove, but you can take it as given wrong. It says if some function is convex, then any function that f is, let's say the function f is convex, then for any random variable, f of the expected value of x is less than or equal to the expected value of f of x. It turns out actually it just comes from the definition of convexity, or alternatively for concave functions, f of expected value of x is greater than or equal to the expected value of f of x. And the way, I can never remember the direction of the inequality, so I prefer to think of it in pictures. You have a function, let's say it's convex. By definition of convexity, if I draw this line here, this line is entirely above the curve below. So let's pick any point in between. So let's say this point here. This point here, the value of the function. So let's say these 2 points are x1 and x2. Any point in between these two is simply the point on the line. So I can write it as lambda 1 x1 plus lambda 2 x2. Right? Oh, sorry, not lambda 2. Take that back. It is, I'm going to write at the bottom so that we can. Any point here is lambda times x1 plus 1 minus lambda times x2. It's just this convex combination of these 2 points, any point in between. And the value of the function here is, so this is this point. And the value of the function is just f of this. Right? That's this level here. The definition of convexity says this point here, is less than the line that connects the 2 function values. So it's less than or equal to f of lambda times f of x1 plus 1 minus lambda times f of x2. So lambda and 1 minus lambda add up to 1. I can think of it as a probability distribution. So this is f of the expected value of x less than expected value f of x. This is just proof by pictures. If you take this to more higher dimensional space, you get this. If you don't get it, then just take it as a given, but there's a question.
What's lambda?
Lambda is any number between 0 and 1. So if you find this to be just too messy, really the only thing we care about using is this quantity. If a function is concave, then f of expectation of x is greater than or equal to e of f of x. that's all we care to use, it turns out log is a concave function, which is convenient because remember the quantity that we had was log of expectation. And Jensen's inequality says log is this f here. Log of E of log expectation of some function, something, I don't care. The ratio is just x, let's just call it x. So log of E of x is greater than E of log x. Right? So let's plug this back in. So we had the log likelihood of the data, and now we have Jensen's inequality, and Jensen's inequality is what makes EM work. Jensen's inequality says the log likelihood of the data is greater than or equal to the sum of the expectation of that ratio. Questions before we move ahead? How many people got it? How many people didn't get it? How many people have hands? Okay. So, I can tell you that the first time I saw EM, I was like, this is just garbage. Because it's just a lot of algebra. The only way to get EM intuitively is actually to work through this yourself. The recipe is going to be identical every time. We want to maximize the log likelihood of the data. We write down the log likelihood of the data. The first thing from here to here is marginalize the y. From here to here this is any q, any distribution q. The next step simply says the definition of expectation. And from here to here is Jensen. Please go over this, when you're back wherever you are, because it may not be the most obvious thing. There's just one more thing to do, which is I just rewrite log. But now we have something interesting. What we have is that the log likelihood of the data is always, for any q, I don't care which q, the log likelihood of the data is greater than or equal to the difference of two things. The expected log likelihood minus, it turns out this is actually like the entropy. This is like an entropy term, but we're not going to worry about it because this quantity here does not depend on theta. Theta is the alpha, p and q that we had before. So we wanted to build an approximation for the log likelihood. And what we have managed to prove here is this quantity at the bottom is always less than the log likelihood. So the general recipe is maximize this lower bound instead. Okay? One more thing and then we can stop for now. What we would like is to maximize the log likelihood of the data. And there is no solution for that because it's not convex. And this whole mess of theory that we had says, instead of maximizing the log likelihood of data, hallucinate a probability distribution Q, some probability distribution Q that says something about the labels, and maximize the lower bound of that log likelihood. This expected log likelihood here minus some other term. We haven't still said what's a good value of Q. It turns out, I'm not going to talk about the details, the last line is what really matters. If I had some estimate, some parameters that I already knew, maybe if I had some alpha, p and q in the coins example that I think is good, then I can use my current probability distribution, current parameters, to produce a posterior probability. Right? This was really scenario 1 in the thing. I have alpha pq, I can guess what's the, or I cannot guess in this case, I can actually estimate what's the likelihood that this coin, this example came from coin 0, coin 1 or coin 2. Using my current estimate, I'm going to use theta t for that. Using my current estimate, I can guess what is a reasonable value for the label for each example. That's a probability distribution over the labels, right? For every example, that's a probability distribution over the label. It turns out, for this particular way of doing things, using Q, the whole thing that we had before was for any choice of Q. For this example, using Q equals the current estimate of your probabilities, or the current expected value of the label is a good estimate. I'm going to stop now because I think this is a lot of information. But I can assure you that you will find EM will forever haunt you if you don't work it out yourself. It's one of those things that needs just, you to write it out and convince yourself that the math on the slides or in a book or whatever is not a lie. So please do that, and we'll continue from here in the next class.